For centuries, the way we control machines has been limited by our own anatomy. Every command must travel from the brain and out to peripheral nerves to trigger a physical movement. This chart illustrates standard interaction design. Even as computing evolved, the input pathway remained the same, relying on muscles to execute human intent. Brain-machine interfaces offer a direct bypass, communicating from cognitive intent straight to an artificial system, skipping the biological periphery entirely. This direct connection requires treating the central nervous system as a raw physical signal source. It means capturing probabilistic microvolt-level biological activity and translating it instantly into deterministic digital control commands. Signal acquisition is the inescapable bottleneck in neurorobotics. A BMI system's capability is defined by its physical method of extracting data from the skull. The starting point for that signal is the neuron, the fundamental information processing unit of the brain. When these cells communicate, they release chemical neurotransmitters across a gap called a synapse. This binding triggers a sudden electrical shift within the receiving cell. This chart illustrates an action potential. Membrane voltage rests in the negative until a stimulus pushes it past a threshold, triggering a sharp spike. Because its amplitude is fixed, it's treated as an all-or-nothing digital event. The wave's shape doesn't contain data. Instead, intent is encoded in timing. Through rate coding, the system measures spike frequency over a time window. A sudden cluster signals a stronger command. Through temporal coding, the system extracts data from the microsecond-level synchronization of spikes across different neurons. Executing a command as simple as lifting a finger requires reading thousands of these timing patterns simultaneously across a vast network of cells. The true engineering hurdle is not detecting a single spike, but capturing a massive population of them with enough clarity to decode their collective pattern. This diagram maps the functional areas of the brain. To find these coordinated patterns, engineers must target specific regions, such as the primary motor cortex, highlighted here in green. Capturing cortical electrical activity means dealing with surrounding layers: cerebral spinal fluid, dura mater, cell, and scalp. Each distorts the data. The fluid acts as a conductive medium, smearing sharp spikes. Hitting the insulating skull, volume conduction forces remaining electrical fields to scatter and flatten. By the time these electrical potentials reach the surface of the skin, they have degraded to a fraction of their original amplitude, often in the microvolt range. Because the signal physically disperses as it travels outward, it becomes impossible for a surface sensor to pinpoint where or when the original spike fired. This forces a compromise. Engineers must sacrifice either spatial resolution, temporal resolution, or the biological integrity of the patient. Electroencephalography, or EEG, is the standard for non-invasive signal acquisition. It uses arrays of electrodes laid out across the scalp to measure the voltage fluctuations making it to the surface. Its primary technical advantage is speed. EEG captures data with millisecond-level temporal resolution, allowing systems to register cognitive shifts almost instantly. But due to volume conduction through the skull, its spatial resolution is poor. The sensors pick up a highly blended noise profile, capturing millions of neurons firing at once rather than specific local circuits. This faint signal is further buried by high-amplitude artifacts. A facial muscle twitch, an eye blink, or even ambient power line interference can drown out the neural data. Even with heavy filtering, EEG is largely restricted to detecting general states of attention or driving low-bandwidth systems like communication spellers. While safe and accessible, the high noise floor makes EEG mathematically insufficient for driving complex, multi-degree of freedom robotic limbs. To improve precision, engineers use electrocorticography, or ECOG. This is a semi-invasive approach where a physical grid is placed directly onto the surface of the brain. By removing the bone insulator from the equation, ECOG restores access to high-frequency bandwidths and clarifies the spatial origin of the signal. However, the grid still records local field potentials, the average activity of thousands of nearby neurons, rather than individual cells. The highest tier of data acquisition requires intracortical microelectrode arrays, the most invasive standard currently available. These devices, like the Utah array, use grids of micro-scale needles to physically penetrate the cortex, recording extracellular action potentials from individual neurons. Capturing isolated spikes gives algorithms the raw data density needed to decode complex vectors. It allows a computer to calculate the precise force, velocity, and three-dimensional direction of a planned movement. The cost is biological. Piercing the cortex triggers an immune response. Glial cells encapsulate the needles in scar tissue, while the saline environment of the brain slowly corrodes the electrodes. High data fidelity currently requires tissue penetration. As a result, the brain's own immune system is the limiting factor for long-term hardware stability. Mapping these electrical modalities reveals the core engineering trade-off. High signal fidelity currently requires high invasiveness. There are alternative methods. Metabolic imaging techniques, like functional MRI, observe brain activity by tracking blood flow. While fMRI provides excellent spatial resolution, it introduces a severe latency penalty, taking seconds to unfold. In Neuro-Robotics, an input delay of several seconds makes a device useless for real-time, closed-loop control. Ultimately, the chosen application strictly dictates the hardware. Driving a high-fidelity, articulated prosthetic requires the spatial and temporal density that only intracortical implants provide. Moving these systems out of the laboratory requires breaking this optimization matrix. We need inert, flexible materials that resist scarring, or new methods for high-resolution wireless scanning that function without an implant. In the interim, engineers rely heavily on artificial intelligence. Deep learning algorithms are trained to extract reliable intent from noisy, degraded data of safer hardware. The success of human-machine integration relies on neuroscience, but it is ultimately an engineering problem. Today, the final barrier to seamless neurorobotics is the physical reality of bridging wet, probabilistic biology with deterministic machines.